Hi, my name is Franz Birknieder, and with this poster, we'll be exploring graph-based ligand binding prediction for residue classification. This work came out of my thesis at Rostlab under the supervision of Kyra Erckert and Professor Rost. To start off, the fundamental challenge of binding residue prediction is the scarcity of experimental annotation. Littman et al. Assembled a dataset from BioLib in prior works, but after homology reduction, only about 1,300 protein sequences remained. Within those sequences, only less than 10% of the residues are actually annotated as binding. And that is further subdivided into three classes of ligand partners, that is metal ions, nucleic acids, and small molecules. Samples for small molecule binding are far more abundant than for the other classes, which gives us an imbalanced dataset to deal with. So first, we need to build graph representations for the proteins. We tried to leverage the 3D structures that are easily available since AlphaFold. The distance matrix contains the distances for each pair of residues in a protein. And whenever the distance is below a cutoff value, we construct an edge between those two residues, and that is captured in the adjacency matrix. From that, we get a graph where each node is a residue, and nodes that are connected by an edge can exchange messages. From the protein databank file, we also extract a secondary structure feature vector via DSSP per residue. Also, using the protein language model PROT5 from Rostlab, we get a per residue embedding vector. And now finally, we combine all of that so that each node in our graph has node features. To sum it up, some of the tertiary protein structure is captured by the graph, while the node features include secondary structure features. Now, our first architecture for a predictor consisted of 2 layers of graph convolutional networks. And we found that with this simple model, we actually matched the performance of the state-of-the-art predictor, BindEmbed 21DL from Littman et al., but with about 80% less trainable parameters. Another nice side effect of this graph network approach was that we could predict arbitrary sequence lengths, while with BindEmbed 21DL, that was capped at about 800 residues. We tested many different graph networks, and with the model that showed the best performance, we started taking away some of the input data to study the effects. Now, if you remember, our nodes included the secondary structure features from DSSP next to the PLM embeddings. When we took those away, prediction performance did not suffer significantly. This suggests that this information is already captured in the embeddings. Similarly, we capture some proportion of tertiary structure by the way we determine adjacency of nodes. We connect to nodes if they're close to each other in the protein 3D structure, so that they can exchange messages. We built graphs from randomly generated adjacency matrices and used those for prediction. The prediction performance also proved robust to this, indicating once again that this information is already contained in the embeddings. So coming back to this slide, with what we've learned, we showed that we can yield the parameter reduction by 80% without actually using any additional data from predicted structures, but simply by using graph neural networks, omitting the DSSP features, generating our own adjacency matrices, and using PLM embeddings. I want to thank everyone at Rostlab for their support and patience, and everyone listening to this for your attention.